So welcome, everyone. My name is Laura Chappell. I'll be doing this session. We're going to be focusing on Wireshark, Wireshark, Wireshark. Some things I want to tell you before we begin this session. First of all, this is a lousy network. This is an example of a really, really bad network. I'm watching the wireless network, and I expect it to be that way because usually wireless networks at shows are really cruddy anyway. You know, we've got too many people, not enough access points. You got huge amounts of data people are trying to download. As I was just looking at the traffic here, I'm listening to all the 802.11 traffic right now that's happening on 2 different channels simultaneously. And I've got the expert window up in Wireshark. And we've got some really incredible errors, but a number of these errors are things that I see every single day on every single network, and it's totally transparent. You have no idea it's happening, and it's causing your network to just die performance-wise. So I'm going to look at some of these packets on the live network here just to kind of show you. We see some ACK loss segments, short segments, retransmissions. All of a sudden, you're going to see this thing come up that says 4 NOPs. Now, 4 NOPs is an expert notification that was added to Wireshark after the SharkFest conference last year. So one of the big things that I've been spending a lot of time doing is analyzing traffic on either side of an interconnecting device, such as a router or a switch or a firewall or something that processes packets, to see how they're affecting those packets. And one of the big ugly things that's been happening is these interconnecting devices are mucking around with our TCP headers during the handshake. They're dinking around with our data, and we don't like that. So I'm going to talk a little bit about it. I'm going to try not to point to any specific vendor, but you may be able to tell just by the MAC address, and that's not my fault. That's just because it sends it from a MAC address that Wireshark recognizes. But all over the place, I'm seeing these same problems occur. And I can see that we're having this problem on the wireless network. Even sitting on the wireless network right now, I am seeing problems because of the wired network configuration. I'm seeing problems because of a router on the wired network. And if I'm a wireless user here, I'll complain and say, hey, the wireless network stinks. It's not the wireless network that's stinking. It's that router on the wired network that's stinking, and that's causing our problems. So I'm going to talk about that a little bit with you. I'll go ahead and I'll stop the capture. What I've been doing is I've been having Wireshark go ahead and just capture all of the wireless traffic. I'm only showing the data frames. That's why I have a display filter up there looking at just data frames. So it's only showing the data frames because those are the ones I'm really mostly interested in right now. It's capturing using a ring buffer. And that means that I've got Wireshark set to capture a set of 10 meg files, and it's numbering each of those and putting in the time and date stamp when it saves those 10 meg files. And I think I have it set for a ring buffer. I don't remember what I configured. Let me go ahead and stop and look at my configuration one more time. I can't remember what. Did I say 10 files? Oh, OK. So it'll remember the last 10 files, 10 meg files. It'll save those to drive, and then it'll keep overriding the older ones. And that way I don't fill up my whole drive. So this is the configuration that I used in this example. And all I did was in the capture area, I put in the file name, you know, big file for fun.pcap. And then I just simply said, I want to use multiple files. The next file is every 10 megabytes, and I want to use a ring buffer with 10 files. So I wouldn't fill up my whole entire hard drive, because I've done that a lot of times. Filled up the hard drive. I say, oh, what happened? I have no room for anything anymore. All right, so that's what I was doing. And I'm going to come back to that in just a little bit, because it's really interesting that what we're seeing here is exactly like what I'm seeing all over the place in the industry. OK, this is the LoRa's Lab Kit. So we just handed a gentleman a LoRa's Lab Kit just a moment ago, the first LoRa's Lab Kit we've given out at this show. It's the 10th edition of the LoRa's Lab Kit. And I want to show it to you because you are all interested in troubleshooting. And there is a very heavy focus on troubleshooting this big, ugly problem that I'm talking about in the LoRa's Lab Kit. I also want to just tell you right now that wherever you see V10, if you click on that, you'll see something interesting. So wherever you see the V10, you'll notice that I've been given the finger, so to speak, up here. So whenever you see that, you can click on that and see something different. I'm going to go ahead and click Explore, and that will take me to the table of contents for the lab kit. In the upper left-hand corner, you're going to see the new videos that I put together. Now, the lab kits are all sitting down at the Global Knowledge booth downstairs. That's booth number 1803. So it's booth 1803, and all the lab kits we brought with us, they are all sitting in that booth. They've got them all ready to go to start handing out. So when this session is over and that floor opens up, you want to get down there and get them because we only brought a limited amount, and I can tell you that there just aren't a lot. After the conference, when I get back, I will put an ISO image up online of the lab kit. But if you want it right now, because of what's in it, you can go grab it at their booth. I want to make sure that all of you get the lab kit by the end of the week, and I want you to learn some of the techniques that I'm using in Wireshark. You know, when you get Wireshark, it is a lump of clay. It is only made really for capturing packets and showing them to you. It doesn't have all the bells and whistles, and it doesn't have the configuration that allows us to really easily spot a lot of problems. Sometimes it does. Sometimes Wireshark will say, hey, you know, there's a retransmission. Well, okay, that's great. But there are so many other problems that are happening on networks today, and Wireshark just won't tell you. So in here, I'm going to build a coloring rule that is going to spot not just the basic problem that we're seeing with interconnecting devices, but the enhanced version of that. There are two flavors of death that these interconnecting devices are causing. Wireshark has an expert notification on one of them already built in. It doesn't have the next one built in yet. So it just started rearing its ugly head a few weeks ago. So I'm going to go through and make sure that I show you exactly how to do that. And I recorded a video on how to do that in the Laura's Lab Kit. That first video that you see is me walking you through the process of creating a troubleshooting profile. It's one of the things that you have to know how to do with Wireshark, and it's one of the things listed in the PowerPoint slides for this set. You need to know how to make a troubleshooting profile where certain things stand out that you're interested in when it's a performance issue versus if it's a security issue and you're looking for a malformed frame or something. So in that video, I will go through and you'll see me creating this custom profile. I've done it enough times in public, created a custom profile, and always had the same comment at the end of it. Can I just have your profile? I don't want to make it. Can you hand it to me? So if you look down in the bottom where it says special stuff, that's the actual troubleshooting profile I made in that video. So if you don't want to make it yourself, you can go ahead and you can import it into Wireshark. And so now you get to the point where you realize Wireshark has no import profile feature in it. Okay? And because of that, the second video up on top is how to import a profile. It will take you step by step. I'll be on a basic Wireshark system, and I need to import that Laura's Lab Kit profile. And you'll see exactly how to do it, the simplest way possible to import the profile. Once you run the Lab Kit profile, the traffic's going to look very different than it did just a moment ago on your network. I can guarantee you, you're going to see a lot of butt ugly orange. Now, I apologize to those of you with orange shirts in the room. And sorry, Riverbed, who now owns the Wireshark trademark. Butt ugly orange. I mean, orange was my butt ugly color before they bought the Wireshark trademark. I'm just really sorry. It's the only color that Gerald does not use in Wireshark for anything, so it's wide open for me to use for my troubleshooting and security colors. Now, the third item down on the lab kit is a case study, interconnecting device hell. That will take you through analyzing traffic on two sides of a device on a network so that you can easily see this is why the traffic is so bad, or why the performance is so bad. I will compare them. I will explain to you what we should have seen if everything had worked properly. And then I'm going to show you how to build a coloring rule so it will scream at you every time that happens. And that's the coloring rule I want to show you. There's also a video on the display filters, doing custom display filters. I don't like the way the default set of display filters looks. It's all just jumbled in there. And what I do is I put in a title and I indent the display filters that are the default. And then I put in a special title for my own display filters. And then I organize them differently. That's just a feature that would be nice to have in Wireshark. You know, sorting your display filters. Why can't I just sort that field, Gerald? Oh, I'm sorry. You and nobody else asked for that, Laura. So if you want something in Wireshark that you don't already see, you have a much better chance of seeing it if you ask for it than if I ask for it. Because I'm always whining and crying to Gerald. Oh, Gerald, you know, it'd be really nice if we had this. He's like, okay, I'll just write that down. And I know he throws it away. All right. So just to tell you where Wireshark is right now, because this week is a big week for Wireshark, in the background, I brought up this interesting view. This is the Wireshark waterfall. This is the BuildBot waterfall showing you how the development of Wireshark is working right now. And today we've already had, in total, I guess, 1, 2, 3, 4, 5, 6, 7, 8, over 50 builds of Wireshark have happened already today. Today's build, we are waiting for all green to show up on the waterfall. Every one of these columns you see is a different operating system that Wireshark runs on. On the far left-hand side, you'll see that's the Windows 32-bit version. Right after that is 64-bit, Ubuntu, Solaris, OS X 10.6, OS X 10.5, OS X 10.5 PowerPC, Visual Studio code analysis piece, and then there's this little cloning piece at the end. A couple of these slaves are new to this process, but when all of these go green all the way to the top, we will have Wireshark 1.6 out. We are just waiting any moment for this to finish up and be happy. So we've got 27 minutes on one of those, 29, 57 minutes. We have 4 hours. Oh, dang. Ubuntu just takes forever. Just slow. Oh, I'm Ubuntu. You know, it's very, very, very slow. But once this all goes green, we will have the new stable release of Wireshark. We will now be in the 1.6 version. Just when you realize that you've downloaded 1.4.6, and you're on the latest version or whatever, I can't even remember because I'm in the development version. But once you've gotten all up to date, all of a sudden you find out, oh, God, now we're changing to a new version. You want to be using 1.6 because of that interconnecting device problem. There are things we can do in 1.6 that we couldn't do in any of the 1.4 versions. The developers are listening when it's somebody standing on stage screaming and crying and complaining about these networks, and Wireshark should be able to show me all these problems automatically. And they're making little tweaks to it so we can start seeing some of these huge problems that we're detecting. Besides that view of Wireshark, you can actually click in the waterfall anywhere and see how each build is doing. But those are today's builds down here. We have 3 builds that are for the Windows 32 platform that have been done, and obviously, in another 7 minutes, another one will show up there. You will see that the builds that are being done, that were done earlier today, it's Wireshark 1.7. So you just upgraded your 1.4.x version. I'm going to be using 1.5.1, which is a developer version. Anytime the next number after the first decimal point is odd, it's a developer version. Okay? It's in development. So I'm on 1.5. Which, when we finally finish the massive builds going on today, will become a 1.6 version. It will be a release candidate as a stable version. You're going to want to grab that 1.6. It's actually a really nice rev. Some of them in the past have been really, really bad. But this one is nice. Does anybody want to guess how many downloads there are of Wireshark every single month? What did you say? You raised your hand. What a good schoolboy. Your mother taught you right. No. How many did you guess? 400,000? No. Guess again? Anybody? 500,000, that's right. It's actually well over 500,000. That's just from the Wireshark.org website. That does not include South Korea, where they get their own mirrors and everybody downloads locally from there. It doesn't include Japan. They've got their own mirror. People download from there. They don't come across and get our version, things like that. And it certainly doesn't include Australia, I'll tell you that. How many Australians are in here? See, they couldn't even make it over here because they're troubleshooting their networks over there. Networks in Australia are so pathetically slow. That's why they're so happy, and they drink beer, and they're like, oh, let's go out and drink instead, because it's going to take me another hour to download that 20K file. Okay. Fine. All right. Anyway, so 1.7 is now in development. So 1.6 is really finished, done. They're just waiting for the BuildBots to go, and then we're going to be moving to 1.7 next. So just when you think it's about done, it's not. All right, also, when you click on the eye of the shark, you will see that you get the finger. When you go up to the eye of the shark on the lab kit, you click on that, something will show up as well. The resources from the Wireshark book, the Wireshark Network Analysis book is down at the bookstore, but we only brought a really small number of copies for them. So if you're going to get a the show discount, you want to grab it from the bookstore downstairs. But there are a number of videos that talk about testing your adapter to make sure, especially in the wireless world, what can your native adapter actually capture? Because you've got promiscuous mode and you've got monitor mode, and they're 2 different things. This adapter right here will go into promiscuous mode, my native wireless, but it will not go into monitor mode. And because of that, I have these lovely antennas up here, and I have my specialized adapters, the air PCAP adapters, because they will go into promiscuous mode and monitor mode. I can capture not only my wireless traffic, I can capture any wireless traffic on any channel, regardless of the network that you're connected to. Because in monitor mode, I don't connect to any one of those networks. I'm listening to all networks. I don't associate with any of them with these air PCAP adapters. So it's really great. If you're in the world of wireless, you need to be able to do that. So there's a ton of stuff that's available on the lab kit. Far right-hand side on the bottom, we did just release our Cafe Press page. So you will see some very unusual items there. And don't get mad at me. Don't get offended. I'm sorry, but sometimes the truth really hurts. So there's just one particular item that everybody in my office was like, oh, don't do that. Oh, don't put that. You can't do that. Well, you know, it's true. So if you are a country and you get offended by people saying you steal everybody's intellectual property, don't go look at our Cafe Press store, okay? All right, so this is what we're going to do in here. Lab kit, I told you already about that. Global Knowledge Booth, 1803. They've got them there. Grab them quickly. Here are the 10 top problems, and we saw a bunch of these in the background on this wireless network. Number one, packet loss. I cannot stress enough how bad packet loss is on your network. And as much as you may know TCP really well, and you know that TCP has a recovery mechanism for that, if you lose 4 TCP packets in a row, your life is hell. 4 TCP packets in a row. Just a slight moment there where there was a disconnect, you lose 4 packets in a row or more, and your life is sheer hell. No matter what version of TCP you are using, Reno, New Reno, Reno with SAC, any version that you are using out there, it is going to go back into this congestion avoidance business. It's going to go back to this, oh, I'll send you 1 packet, and then I'll wait for you to acknowledge that. And then I'll send you 1 packet, and then I'll wait for you to acknowledge, and I'll send you 1. Oh, it's hideous, and it's painful to go through. You want to do everything you can do to stop packet loss. And where does packet loss occur? 99.9999999% of the time, it's going to be those damn interconnecting devices. Very rarely will a server go, oh, here's packet 1, packet 2, here's packet 4. You know, they don't do that. You know, packet loss occurs on those interconnecting devices. And our TCP stacks today, every TCP stack that's out there makes an assumption that when packet loss occurs, it's going to be congestion. Now, how are we going to deal with this congestion? Well, we need to slow things down. I'm going to show you a trace file that shows you how bad packet loss can be. Now, this is a trace file that I have not given out. So you will not see this particular one on the lab kit. Let me bring it up on this system. Hang on. All right. I just popped it into a directory here. Okay, it's a, pardon? Oh, I have to, I'm sorry. Thank you, you have to tell me. I have never presented before. You know what? I love dealing with troubleshooting. I think it is fascinating to see what's on people's networks. And I used to work at Novell a billion years ago. And I left in 1993. I started my business. And one of the first things was people were asking me to come out with our Lanalyzer product and come and analyze their network. And I was scared to death because I thought, oh, gosh, what if I go in there and they're all standing around me and there's nothing wrong? Well, that was 1993, and I've never had that issue ever. There's always something up. In the bottom right-hand corner, you're going to see that I'm working in the LLK10 profile in Wireshark. I'm working in a profile that will highlight where there are problems. There's my, it doesn't really show up orangish on those screens, but it's really a darker orange on mine. But you can see there's some packets that have a problem. When you get into troubleshooting, the first thing you want to do, place the analyzer appropriately. Golden rule number 1, place the analyzer appropriately. Do not start capturing traffic inside the enterprise in the middle of it somewhere. Don't start capturing traffic at the server. Go to the client. Go to the user that's complaining. There are too many times I go on site, and it's like, you could have seen this problem. but you capture it at the server instead of the client. So all of the round-trip time values, everything you're seeing is from the server's perspective, not the user that's complaining. So you want to get as close as you can be to the user that's complaining or the device that's complaining or whatever it is. You want to be as close as you can possibly stand being to that user and capture the traffic from there. Once you do that, as we did in this instance, once you do that, I want you to build an I/O graph. I want you to start with the I/O graph. So with this trace file, this is just simply somebody going and downloading a 100 meg trace file, or 100 meg file. They're just doing a test, a throughput test. So by just selecting statistics, I'm going to go to I/O graph. Now this is a pretty big file. This is 119,000 packets in it. So it's this big, long file. And I'm only using the 32-bit version of Wireshark. The 64-bit version would be faster here. But the 64-bit development version has had a couple of problems with it, so I stayed away from that. In 1.6, once it's out today, then I will definitely do that. All right, here is this user just basically saying, hey, I want to retrieve this file. Everything looks really, really great at the beginning, and then all hell breaks loose here. Look at this. All of a sudden, we have a drop in throughput here. Goes back up. This is an automated process. I mean, this should be just boom, big, high, spiky mountains, but they're very few mountains. We never want to see low, rolling hills on here. That's Australia. All right? Okay. I love Australia. I love it, love it, love it, love it. I just would rather, mail somebody information on a USB stick than use the internet there. All right, so I'm going to just click on the I/O graph wherever I start seeing it go down to a very low throughput rate. And in the background, Wireshark is going to highlight the packets at that particular point in the I/O graph. I do not want to troubleshoot high throughput. I want to troubleshoot low throughput. So I'm picking where all of a sudden it started flatlining. And in the background, you are seeing retransmissions, 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 retransmissions. The problem that happened in this trace file came because of packet loss. In this trace file, getting a big fat file down, there is a point where the sequence number jumps in TCP. All of a sudden, we're getting this sequence number, and then the next packet that came in was a much higher sequence number, and Wireshark looks at it and says, there should have been some sequences in there. We've got some packet loss that happened here. We've lost a packet. Okay, Wireshark will tell you, we've lost a packet. But if you were to go to the top of where all of this problem starts occurring, oh, here it is. If you go to the very, sorry, I went a little faster. If you go to the top of this, you can see Wireshark says, hey, you know what? The previous segment was lost. If we do a little math between the previous packet and this packet, if we look at the data packet right here, and we go into the TCP header, and we look at the sequence number, then we go to the one where it says previous segment lost. If we did subtraction, we subtracted the lower sequence number for the higher sequence number, what you would find out is that not a packet was lost, but 570 packets were lost in one shot. In one moment, 570 packets are lost. And the interesting thing about this whole thing is, at 4 packets lost, you're going to have a hellish nightmare on your network. And this is 570 packets lost. You need to rebuild this network, whatever's happening here. It needs to go away. You need to take the day off, or maybe, I don't know, get another job, get another life. Don't troubleshoot this network. This is absolutely horrible. So you want to watch for that. Anytime Wireshark says to you, hey, the previous segment was lost here, make sure you do the math to say, well, was it just one segment, or was it 4 or more segments? Because we will recover much more slowly. Everything slows down after that. No matter what TCP stack you use, it's going to be slowing down for you. And that's exactly, look at this. When you see this, this is 1 packet sent and 1 acknowledgement back, and then 1 packet sent and 1 acknowledgement back. Because we lost so many at one time, this TCP host is going to go into this horrible, horrible congestion avoidance mechanism. Do y'all remember learning TCP, congestion avoidance, slow start? I'm sorry, it goes into slow start, not congestion avoidance, excuse me. So it goes into slow start. Do you remember learning all that stuff at the beginning when you were just learning about TCP? Because if you didn't learn it, you need to learn it. You need to understand how we deal with packet loss and recovery. You should all know selective acknowledgement is a good thing. You should all know that window scaling is a great thing, except for those crappy interconnecting devices that screwed up for us. Okay? There are some things you should know about TCP, about how it works. And you're going to see that in the lab kit videos. I have a lot of stuff on that. So I'm going to blaze through the slides here because I'd rather work live with the packets. Okay, client, server, and wire latency. 3 places where we can find latency. The easiest way to see if you've got wire latency, just capture close to the client and have that client go make a connection to somebody. I don't know if it's web browsing or whatever. Look at the very first packet in your trace file, the SYN packet, and then look at the SYNAC that came back. You have an approximate round-trip time to get a packet to that target server and get a response back. That SYN didn't have to go up through the application and get processed and all that stuff. It goes just to the TCP stack, and you get a SYNAC back. Or even if it's a reset, it doesn't matter. You just got your round-trip time values. All right, server latency and client latency. If my client says SYN to a server, the server comes back, SYNAC, and the client goes ACK. And then we wait. And then the client says, oh, get me this. All right, that's client latency. You stupid client. The whole reason the connection was set up was because you wanted to do something. You started the connection. Immediately after the third packet of the handshake, you should have talked. One of the things I'm seeing now is that we're seeing data in the third packet of the handshake. A lot of instances where data is in the third packet of the handshake. It will work. It's not very pretty. It doesn't really quite match the spec exactly, but it will work. It's just not great. So don't be weirded out when you see SYN, SYNAC, data. That data packet will have an ACK, and the handshake will be completed from that. Server latency. The client goes SYN, the server goes SYNAC, client goes ACK, client goes get me the first page, and the server goes ACK, I got your request. And here's the data. Okay, that is server latency. What is taking that server so long? One of the big things that happens now with the way networks are architected is when I ask for something from the server, I'm not getting it from that server. That server's got to go get it somewhere else. And that causes the server latency. So before you point your finger to that server and say, oh, your dog's slow, you got to look and see, is that data local in that server? Or is it going out and asking somebody else? Perfect example of this is Outpost.com, Fry's Electronics website online. When you go and you say, I want to look for laptops that have pre-installed Windows or something like that, you go and you look that up. It's a very slow load process. It's like, oh, their server is so stinky, lousy. No, it's actually because that server is talking to a slow, stinky, lousy other server. It is really. They have a background server back there that's just absolutely horrible. Okay? But it's not the first server in the path that's the problem. It's the second server in the path that's the problem. And that's why we have to use more than one instance of Wireshark sometimes. Window scaling. All right. In an ideal world, anytime I go to any one of your networks and I watch the communications, every single one of your systems is using window scaling. And you're not having any problems because of it, and everybody's happy, and we're into this new world. If you don't know about window scaling, RFC 1323 is what you want to read. Without window scaling, you have this little tiny paper cup of received buffer space. It's only 65,535 bytes of space by default. And when you do the handshake, you go, oh, hi, I want to make a connection, and oh, just so you know, I have this little tiny paper cup worth of space, and you can send traffic to me only until that cup is full. As our links are getting faster and faster, and the files that we're opening up and downloading are getting bigger and bigger, those little tiny paper cups are not sufficient anymore. Not only that, but you're running more and more intense applications on your workstation, and the application that's asking for the big amount of data doesn't have the time to go down and pick it up all the time out of this little tiny paper cup. I mean, the paper cup's getting full so fast, it doesn't have the time to do that, so the application is sitting there going, I'm doing the best I can, doing the best I can, and you find the workstation start saying Windows 0, Windows 0, Windows 0, Windows 0, I don't have space. And the other side of that communication has got to stop sending data. It's got to stop sending data. All of a sudden, it's just boom, nope, nothing, and the client's sitting there going, Windows 0. The other side might say, well, are you still at Windows 0? Yep, Windows 0, hate you, go away. But I thought we loved each other. Nope, I always hated you. Hated everything about you. But what about, oh, never mind, I love you. Here, I have a little more buffer space, okay? That's called a window update process in Wireshark. And one of the problems we have right now in Wireshark is that the window update problem is seen as or the window update packet, excuse me, is seen as a problem when it's not. It's a good thing. We always want to see window update packets. We love it. It means that somebody just said, hey, I've got a little more buffer space. But we're still working with that stupid paper cup. What I want to see ideally is I want to see your system send out a SYN packet, and in the TCP header there's an options area, and I want to see your system say, I support window scaling. And this is the big, huge number that you can multiply my window size field by from this point on. That means you took that little tiny cup and you said, oh, you know what? Actually, I have 256 of those cups. And until all 256 are full, and I tell you that, you just keep sending me data, keep sending me data. And it's fabulous. But for window scaling to work, I send the SYN packet across and I say, 256 times whatever I say, I support window scaling. If the other side turns around and says, oh, what the hell that is, I'm just going to synac back, then we're not allowed to use it. Either both sides support window scaling, or neither side can use it. So you sit there and you go, okay, well, forget you, you're a lousy configured OS. I'm going to do a TCP handshake to another server, window scaling, take my Dixie cups, and I want you to multiply it times 256. That's how much space I have. Server on the other end goes, that's great, you know what, I also support window scaling, but you can only multiply my window size field by, let's say, 16, but I think that'll be okay because you're not really sending me stuff. You know, I'm the server, I'm sending you stuff. So, synac, this is what I can do, multiply mine times 16. And there's that dang interconnecting device going, nah, I don't think so. I don't feel comfortable with all this. So what I'm going to do is, when you say you can support window scaling at 256 times whatever the cup size is, I'm going to change that. I'm going to either strip it out completely, and if you don't talk about window scaling, the server never will, or I'm going to change it to allow a multiplier of 1. So you send this packet through and you say, hey, window scaling, and multiply mine by 256. The router along the way goes, nah, I don't think so. You can multiply it by 1. The server gets it and goes, oh, well, at least you support window scaling. That's really great, I guess. But from the server's perspective, it's only going to take your window size field and multiply it by 1. From your perspective, you're taking your window size and you're multiplying it by 256. So when you start advertising something like a 515-byte window size, you believe it's 515 times 256. But the server believes it's only 515 bytes. If that server has queued up to send you a full packet size, let's say it's 1,460 bytes of data, it's got it queued up to send it to you, and you send it a packet, and the interpretation is you only have 515 bytes, what will the server do? Sending you 515 would be nice. No. The server will sit there and go, all right, I'll wait. All of a sudden, you see data flowing and then stop. Absolutely dead. And then all of a sudden, you'll see a window update packet, hopefully eventually from the client. It'll, at some point, the application will take the data out of there and it'll allow it to go higher than this bogus 515 number, high enough, and then you see the data flowing and then stop. And data flowing and then stop. I can't tell you how often this is happening on networks everywhere, and it's totally transparent to you. There is nothing at that router that says, you know what, I'm going to really screw up the network today. I'm glad you paid all that money for me, and now you're going to pay for it again. There's just nothing that says that. The only way to know this is happening is to start grabbing those packets. So I'll show you something on that. Service response issues, application behavior, poorly behaving applications, there are a lot of them. I said this earlier today. If you're an application developer, you better take the traffic of your application running before you roll it out. There are too many lousy, stinking applications in the industry, and there's no excuse for it. When I see it on the cable, it's like, why did you design it that way? Oh, because you never looked at it on the network. Okay? Network design issues. I have a customer at a branch office. The DNS queries go to the corporate office to be handled by the corporate office. So, and by the way, that's intentional. This particular IT team is very unusual. They seem to make themselves more valuable by screwing up the network and then fixing their own screw-ups at this particular location. It's like, why would you configure it that way? Shh, don't tell anybody. Don't tell anybody, because if it's a really bad day and we're all going to get in trouble, we're going to change it so the DNS resolution is local and faster, and they're going to go, oh, you guys are great. Okay, that's bad. Other network design issues from the west coast of the United States. When I try to connect to a server in Australia, my packets on one of our internet connections, our packets will go from the San Jose area to Sacramento first, which I don't know why. I don't know why anybody would go to Sacramento. I mean, Sacramento is just like basically a dust bowl in California. I don't know. So our traffic goes from San Jose up to Sacramento, back down to San Jose, down to Los Angeles, and then from there it goes under the Pacific link, the fiber link, zooming. And all of this is very fast, and zoom, zoom, until you hit Australia, and then it's put, 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 put. You know, it's very slow. But there's no reason for us to do this crazy path stuff. Okay, path issues. If you have not kept up with the packet structures and what's happening with TCP/IP, I want you to be very well aware of, oops, sorry, let me go to G there. There we go. I want you to be aware of a field that's been updated in the communications. And I'm going to open up a trace file that's on the lab kit. This trace file is voice over IP. So it's called VoIP dash, I think it's just VoIP dash extension. Yeah, that's the one I'm going to open up. Okay, when you look at this communication, especially with VoIP, I want you to go into the IP headers of your communications. No matter what it is, I want you to start looking in the IP header. And in that IP header, you're going to see in the olden days, we used to have something called the precedence and type of service bits. How many of you remember that? Am I the only person with gray hair here? Oh my God, that's terrible. Does anybody remember ArcNet? Oh, okay, I feel better now. Token ring? Love token ring. All right, so in here we used to, and if you go to schools now, that's how you can tell whether they're teaching modern stuff or not. If they teach you type of service and precedence, you need to find a different location to take your classes at, because that is not the way TCP/IP works. In the IP header, those fields have been replaced. Now what we have is we have explicit congestion notification and something called the differentiated services code point field. Here is the field. If that field is set to all zeros, it means that you have default priority for handling along a path. If it's something other than 0, you have a higher priority than other traffic along a path. And on the internet, I can tell you, every single router on the internet pays attention to the DSCP values. And a lot of your routers that you install at your networks, they come up and by default, they're looking at DSCP. I don't care what you did in your prioritization based on ports. No, that's what your traffic's going to get prioritized on. Okay? So what I want to show you is one of the things that you can do with Wireshark. And this is in the bullet list. I have just a bullet list in the slides. But you can right mouse click on any field and say that you want to apply this as a column. And what you're going to see right here is asynchronous quality of service. We have a phone right here, and let me move this one over just a bit more. Oh, if that's for me, will you tell them I'm presenting right now? If you don't have your cell phone turned off, you need to turn off your cell phone. Oops, I better make sure mine's off too, or I'm going to get in big trouble if mine goes off all of a sudden. All right, mine's off. Okay. All right. If somebody's cell phone next to you goes off, just point. Okay? And I'll take care of it. All right. Point and run, actually, point and move, because I don't throw things very well. All right. So the very first packet you see in this trace file, this is a phone talking to the call manager. And the traffic from the phone to the call manager has assured forwarding. But the call manager back to the phone has default, lower priority. That's true in the SIP traffic up here. And then if you start looking at the RTP traffic, you will see that the phone to the call manager is expedited forwarding. And the call manager for RTP, coming back to the phone, is default. When you run Wireshark, I want to see you do some customization. I want you to change it so that you have different columns that show you what's really going on. And that's one of the ones always I have on for troubleshooting these days. Okay, itty-bitty stinking packets, you've got to know that to go to the grocery store and pick up each item individually and bring it back to your house and go back and forth is much slower than going in a car and grabbing all the groceries at once and bringing it back to your home. Same type of thing. Fragmentation, I do not like fragmentation. I do not like to see IP fragmentation on the network. I also do not like to see links that only handle small packet sizes. They cause us problems. Timing problems, VoIP calls. Think VoIP calls on timing problems. And infrastructure devices is huge. So, and you'll see, I'm going to talk. Here we go. This is the list of skills, and I'm going to do each one of these for you as I go through. Adding columns quickly. In the PowerPoint slide set, I have a list of the columns that I would add. And let's begin. I'm going to have to go ahead of myself here. All right. I'm going to go ahead of myself. One of the points coming up is to make a profile, to start working in a profile, because Wireshark's default settings are not set for troubleshooting efficiently. So this is it. I'm going to build a brand new, profile for you. And this profile is going to be called, I don't know, TR-TechEd. So I'm going to select Edit, Configuration Profiles. I did this morning with a security profile. I'm going to select New, and TechEd TR, all in capital letters. That's the one. I'm going to say OK. Don't ask me for this profile, because you're going to know how to do all these different things, and the lab kit's got the video of how to do it. The first thing it did was it went and it pulled my default personal preferences, which are terrible because my eyes are not that good. I need to go to a bigger font size. I also do not like the fact that the number column goes right up against the time column. So I'm going to right mouse click on that column heading, align it left. The time column is not set properly either, so I'm going to go into the time column in just a moment. It's another one of the bullet points. But what I want to do here is I want to add some columns that allow me to troubleshoot faster. The first column I am always going to add for all communications is going to be a window size column. Now that trace file has no window size field because it was all UDP. You will see window size in TCP communications only. So I'm going to open up a trace file called TCP- and problem A. Actually, I'm going to open up problem B. Why not? I'll open up this trace file, and I know I've got TCP traffic in there. And in the TCP header itself, I'm going to go down to where it has the window size field. Now, I mentioned this morning. This is a change that we have in Wireshark. When you go to 1.6, I'm in the development version 1.5. It's going to be 1.6 later today. But when you go to 1.6, you're going to see two window size fields. You are going to see the first one, which is what's actually being advertised. And then after that, if window scaling is being used, you'll see the scaled value in a second field. Prior to that, Wireshark would always just show you the scaled value if scaling was in use. And you'd have to do the math to figure out what the original value was. It was a pain. In addition, one of the big changes for those of you that have been using Wireshark for a while is in the protocol preferences, you will see that analyze TCP sequence numbers has been broken away from turn on window scaling calculation. You can't turn off Wireshark's window scaling calculation anymore. If it sees its window scaling, it'll always put it in there for you, which is great. So those two pieces have been broken apart. All right, but that's, oh, I heard my mic drop out for a moment. I was all alone. All right, but what I want to see is I want to see the calculated window size field up as a column. So I'm going to right mouse click, and I'm going to apply this as a column. Always, 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 always put that one in there. You are going to need it. I'm going to change the alignment so it's left aligned as well. I don't like the length column being right aligned, so I'm going to left align that to move these things apart. As I look through this trace file, I am going to add one more thing to it. I'm going to change the time column setting always, always, always. So let me show you the list of things I would change in a troubleshooting profile. I usually put a sequence number column up on top. I usually put an acknowledgement number column up on top. When I send a TCP packet to a target and I say, I am on sequence number 724, and I've got 10 bytes of data, Wireshark will tell me what this sender's next sequence number should be. Wireshark will always tell you, oh, the next one should be this value. In addition, the acknowledgement number field is what I think the other side should be sending me, the next sequence number I expect from the other side. So I always want to watch for when these things might get off. These interconnecting devices, for security purposes, sequence number randomization. It is the gun and the target that sits inside of the router box when you unwrap it. And there's a little instruction there that says, aha, here's sequence number randomization. That's the gun. Please place the target on your foot and shoot yourself when you turn this on. It is absolutely ludicrous. The minute you turn on sequence number randomization, you have killed selective acknowledgements. You are back 10 years ago in performance. Absolutely awful. Do not turn that on. All right, distributed services code point. You saw me do that a moment ago. If you're working with wireless traffic and you capture the packets with an ARP cap adapter, you're going to have some extra headers in there. You're going to have either a radio tap header or a PPI header. And you set up the ARP caps to add those headers. And in those headers, it says what the signal strength was when the ARP cap adapter captured your traffic. So you can walk around and you can actually see the signal strength of the traffic degrading as you move further and further away from the access point. But you can put that up as a column as well. All right, I already showed you this one. Like I said, the slides are really just bullet points. I already showed you this one. Click on the high points, click on the low points. You'll be able to spot exactly why something is a problem. I'm going to do that in just a moment on another trace file. There are two trace files side by side. One is called HTTP download bad. The other is HTTP download good. When you look at the y-axis that Wireshark builds on the I/O graphs, that will tell you how bad really is. If Wireshark has to put this, this axis and it's only going up to 200 packets per second, that's pretty bad. Okay, that's lousy. All right. Now, I'm going to go back to my profile and I'm going to start fixing it with all these other things. Watch the checksum errors issue. My machine right here, whenever I capture my own traffic on the wired network, using the wired adapter, my machine does something called task offloading. And do not turn off task offloading. It's a good thing. But what happens is the application sends the data down to the TCP IP stack. TCP and UDP on my machine, they will inject a bad checksum value in the TCP header or the UDP header. It will not calculate the checksum. That's one of the tasks that's been offloaded. And it's been offloaded to my network interface card. So my TCP IP stack will not calculate a TCP header checksum or UDP header checksum. It's just junk in there. Then it sends it down to IP, v4 or v6, and my system does not calculate the IPv4 header checksum or the IPv6 header checksum either. So it's a bad checksum here. This is, when it goes out on the cabling system, the driver itself passes it through to the card, and the card puts on all those checksums. We have offloaded checksum processing out to the cards, and we like that kind of stuff. The problem is when you analyze your traffic with Wireshark, this is when Wireshark got the packet. It picked up the packet going outbound from your machine when the correct checksums hadn't been placed on it yet. So when we work in Wireshark, all we see is bad checksum, bad checksum, bad checksum, bad checksum. Every packet from my machine has a bad checksum. Oh! And there was a couple of guys earlier that were talking to me about this going, oh, you've got to be kidding. They were having problems with a product on their network, and they went to the vendor, and they said, look, we got problems, and the vendor said, give us a trace file. They sent them a trace file. The vendor opened it up and saw all bad checksums and said, oh, it's a problem with your system. You have a problem with your system. It's your network. Your network is a problem. No, it's not. Our network does checksum offloading. So back in Wireshark, what I'm going to do is I'm going to turn off Wireshark's checksum coloring rule. I believe I have a trace file TCP dash. I don't think I do anymore. Well, you'll know if you have checksum offloading. If you would like to know, this is where you have a great advantage running Wireshark on a Windows host. You'll see that this option doesn't show up yet on the Linux hosts. But in Wireshark, the very first button on that icon toolbar, it will show you all the interfaces. And when you look to the right here for an interface, there's a details button. So you'll see a few other versions of Wireshark on different operating systems. They won't have that. But I'm going to click on this one that says Microsoft. I'm going to click on Details. And if you see Task Offload darkened, it means that for that interface, you support task offloading. So there's one of my interfaces. I'm going to click on the other interface, which is my Ethernet adapter. And look, task offload up there is darkened. So all it's doing is pulling the data up off the card, and it tells me it will do task offloading for IPv4, TCP, UDP, and it will not do IPv6 task offloading. It won't do checksum offloading for that one. Okay? All right, so when you bring up a trace file and you see that every packet one way has bad checksums, if the other side was talking back to you, then they couldn't have been bad checksums. It's just that checksum offloading was set up. So I'm going to turn off that coloring rule so I don't start troubleshooting something that isn't a problem. I just clicked on the little color button up there, and I'm going to go to checksum errors, and I'm going to disable it. If you wish, you can also go into TCP preferences, UDP preferences, IPv4 preferences, IPv6 preferences, and tell Wireshark not to even calculate the checksums. And that will really get rid of anything that might show up and make it appear that there are checksum errors when there aren't. Very rare to see checksum errors happening around the world. All right, so I've just set that one up. Okay, next thing, create a custom profile. Okay, I already did that. I should have put that as number one, the first thing you do, create a custom profile. Because I'm working in this custom profile, my display filters, my capture filters, my coloring rules, my preference settings for the protocols, all of those things are saved in this profile. And you know what? It's just a set of text files sitting in a directory. So let me show you where my profile is. So when you want to start sharing profiles with other people, you can do it very easily. The profile I created is called TechEdTR, and I'm going to go up to Help, About Wireshark, Folders. That tells you where everything is for Wireshark. And your profiles that you create are part of your personal configuration. So that's where you want to go. There's my personal configuration, and there's a profiles directory. Now, this directory will only be made when you make your first custom profile. If you haven't made one yet, it doesn't even sit there. It doesn't even exist. Okay. So I'm going to go into that, and there are all of my profiles. And down here, there's my TechEd-TR profile I just created. And there's my color filter setting with checksums turned off, and my preferences for what the column names are and the size of the columns and all those different things. And if I want to share that with you, literally all I'm going to do is I'm going to hand you that folder. And you're just going to copy it into your profiles directory, and you're ready to go. When you want to move between profiles, you simply go to the bottom right-hand corner where you have that status bar, click on it, and just move to the next profile that you want to work on. So I have different profiles for wireless traffic and wired traffic and this customer and that customer and security and all different types of communications. I build separate, specific profiles so that I can just open up any trace file and it's all custom made, ready to troubleshoot. All right, so that's an easy way to make your profiles. Okay, set the time column properly. Always, 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 always. And this I even do in the default profile at customers. I'll just tell them, just do this in the default. The default setting for Wireshark is to show you when each one of the packets arrived compared to the first packet in the trace file. And I don't care when they arrive compared to the first one. What I want to do is I want to look for large gaps in time. Here I've got one client connecting to a server requesting to download a file. I want to know that there's no big gaps in time. The time column here is set to show you when each one of these arrived compared to the first one. But instead, I'm going to do View, Time Display Format, and Seconds Since Previous Displayed Packet. Because I've done that, I can easily see that I have a 5.2-second delay. And by the way, when everybody's finger pointing, the only finger that matters is the finger of the protocol analyst. Because everything else is junk. Everybody's guessing, you know, the client guy is pointing at the infrastructure guy, who's pointing at the server guy, who's pointing at the vendor. The packets will never lie. They will always show you where the problem is, but they may not tell you why the problem exists. So when this user is complaining right here, because I set that time column properly, I can now sort the time column and see all the large gaps in time and look for anything that might be similar amongst those large delays in time. I'm going to click on that heading once, twice, and I'm going to go to the very first packet listed. And there are my large gaps in time. My finger has just pointed towards the client here. What is going on? You have these big delays every time before you do a GET request. We see a big delay. And we can only do this because we've set the time column properly, and now we can just click on it twice and see where the big delays are. I'm going to give you a really great tip here that will save you time. Do not troubleshoot large delays before any packet that has the fin bit set or the reset bit set. Don't troubleshoot large delays before that first packet. By the way, this trace file is on the lab kit. It's called TCP-problem-point B. There's point A, point B, and point C. They're all part of a case study on the lab kit. So you can open any of those up and see this. That first packet that shows up, I am not going to care about it at all because that's transparent to a user. When you see a fin packet go out, it just means that somebody is saying, OK, I'm finished with what I'm doing, whatever. And apps will sit there and wait a little bit and go, oh, that's right, I don't need that anymore. Or let's go ahead and send the fin bit across to say we're finished. Or the app will all of a sudden say, oh, you know, I think we're done. She hasn't asked for anything for a while, so let's just send the reset bit. But the users have no idea how long that's taking. They don't care. So don't troubleshoot time delays before any time a fin bit is set or a reset is set. Don't pay any attention to those. All right, so in this trace file, I can see that I've got a problem. Every time before that client makes a GET request, we've got this big delay. So that's what I'm going to be working on. It's like, wait a minute, something is happening when this client is trying to make the request. There's a big delay before every request. And it feels to me like it's the client that's at fault here in this trace file. If you want to go sort back by the original, just click on the number column heading. Ow, some of these delays in this trace file are just absolutely awful. Okay, so we've set the time column properly. All right. In Wireshark, you have the capability of having Wireshark resolve names for you. So instead of saying it's www.microsoft.com, or sorry, the IP address of the target, it'll say www.microsoft.com, or it'll say, you know, Fred's workstation, or whatever. Wireshark can do that for you, but be very careful. When Wireshark does name resolution, by default, it will look at all of your port numbers, and it has a services file in the Wireshark program files directory. There's a services file. That's why people go, oh, I hate this because it's showing up Blackjack as the application for port 1024. And I know we're not using Blackjack. Go into the services file and delete that line if you want. You can edit the services file all you want to do. It's just used for Wireshark for the display purpose, and it doesn't take up time. There is a MANUF file, manufacturer file. When Wireshark sees the first 3 bytes of a hardware address, it resolves it for the organizational unit identifier and tells you this is Cisco, this is HP, this is Apple, you know, whatever. So it shows you the vendor. Doesn't take any overhead. But then there's network name resolution. And when we want to set network name resolution in here, we go up to a couple ways of setting it. We can go to View, Name Resolution, and there's Enable Network Name Resolution. If I turn this on, automatically Wireshark's going to look at all the IP addresses seen in this trace file. And it is going to first look for a hosts file in the Wireshark program file directory, a Wireshark hosts file. And if it sees the name and the IP address, it'll pop it right up to Wireshark and everything's fast. But for all of the IP addresses it doesn't recognize, it will do an inverse DNS query to whatever the local system's DNS server is. Can you imagine what would have happened to the DNS server we're all using if I picked up all that wireless traffic with name resolution enabled? I would have killed the DNS server, and nobody can get anywhere, because Wireshark will just hammer it. By default, it would look to do 300 queries at a time, chunking them together. And every source IP address and every destination IP address will be looked up. So if you are going to use a hosts file with Wireshark, because you like to see names instead of IP addresses, make sure that you're very careful of the trace files you open up. By the way, a customer can send me a trace file. And if I have this on, and I open up that trace file, I'm going to nail my DNS server at my company. Everybody's going to go, I'm just going to go all to hell in a handbasket. All right. So on here, you'll see that's what an inverse query looks like. If you want to know if Wireshark is doing all this stuff, you'll see all this pointer, 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 pointer. It's one of the ways that we detect one of the users on the network running Wireshark, because they don't know how to run it right. Don't talk to your users about Wireshark. That's the last thing you want to do, because you know they're going to be coming into you saying, you know, I was picking up my traffic at home, and I was wondering what TCP/IP is all about. It's like, I hate that when people can't say TCP/IP. You know, it's only 5 letters. If you can't do that, you shouldn't be talking about it. It's terrible. All right. There is something called the manual resolution process. Now, I want you, even though it's really, really great, I want you to be aware it's only temporary. And unfortunately, right now, when you use this feature, you're going to have to turn on the really big, ugly name resolution. So be careful, careful, careful if you use this. Here is the feature. In the packet list area, I'm going to right mouse click, and there's an option there to manually resolve an address. It puts in the IP address, and I say, oh, Fred. And I say, OK. It didn't do anything for me, because not only do I have to say Fred, but I also have to turn on that ugly inverse query stuff. So I'm going to right mouse click on this, say manually resolve it. I'm going to put in Fred, and because I know there are only 2 IP addresses, I'm pretty sure, in this trace file, I'll go ahead, and it's late anyway. If I kill the DNS server here, it's the end of the day. You shouldn't be looking up stuff, probably. All right, so I'm just going to say OK. And that's what I see, which is really nice. A lot of people really like to see the names instead of the IP addresses. But that is only saved in cache. So when you restart Wireshark, you've lost those resolutions. And if I just happen to use 10.10.0.1 on one trace file, and then another customer's trace has the same address, the other customer's trace is going to show up as Fred until I restart Wireshark. Boy, I'm going to make sure I turn off network name resolution before I kill the show network. I try not to, usually. There have been some bad instances it shows, and so I'm not there the next year. You know, it's kind of like, what happened? You got really busy? Yeah, I got really busy. So did the network at the last show. Did you notice that? All right, so I try to be good. Okay, let's go back to the slide sets and the checklist here. Okay, so keep in mind that if you are going to use name resolution, try to get a hosts file in the Wireshark program file directory and have it look there. Don't go and kill the DNS server. You should understand the expert info composite. In Wireshark, and if you have the Wireshark network analysis book, there's a whole chapter devoted to the expert system. As I'm looking at this, I don't want to look at this trace file. I want to look at the live traffic trace file. There. This is the wireless traffic that I picked up. Where you see that black background there, that is one of the coloring rules that indicates that there's a problem with that traffic. In the bottom left-hand corner, you'll see this little red dot, and that's actually a button that links to the expert. And depending on the color of the dot, it will tell you how bad this problem could have been. Clicking on that dot brings up the expert window. And in the expert window, oh, let me get that out of. I don't want to do that. Oh, it's the other instance of wire. Oh, don't tell me. Don't. That was such a pretty trace file. Yeah. Well, this is the development version, so it will crash with the larger files, and those were only 10 meg files. The other ones that we have, the stable versions, are really nice. Now, where did I put those trace files? Dang it. Let me go into, were they in here? No. Dang it. I'm just going to have to capture again. That's all there is to it. So I'm going to go ahead and capture the wireless traffic again because I'm too lazy to look around my drive. The very first button will show me which interfaces are active, and I'm just going to pull that aggregator. I'll go ahead and start. There's our wireless traffic. I know we're going to have bad stuff in here because the wireless network here is just really, really ugly. So I'm going to stop the capture now. Well, no, I'm not. While it's capturing, I'll go ahead and open up the expert. Okay, so it separates out the problems based on whether they are errors, warnings, notes, or chats, which is just basically Wireshark saying, well, somebody made a GET request, and this is what they asked for. Somebody did something else, is what they asked for. In the errors section, there's the bad checksum stuff. Now, in wireless traffic, it's not uncommon to see bad checksums on packets that are coming towards me because the signal's so strong, signal's so weak at that point that you've got all this, they're just garbage by the time they get to me. But the beginning of the packet is enough that Wireshark can see it. When you see malformed packets, typically, it's either a protocol has gone out of spec, and it's putting in a value that Wireshark just says, I don't know what the heck that could be, or it's just the Wireshark dissector's got a problem. But it's very common to see this on wireless networks. Same kind of thing. By the time we get the packets, some of them have degraded so much that Wireshark's like, I can't quite put that all together yet. Not sure what to do. So wireless networks, those two, I don't really bother about it. I do have some packets that appear to be malformed for other reasons, but I stay away pretty much from the errors because those are mostly dissector problems with Wireshark. Now, over here, we have a classic Windows 0 condition that is showing up. So I'm going to stop capturing in the background, and I'm going to toggle over to the expert. You should understand that when data is being sent across the network, TCP is the one that has all these expert notifications in it right here. Retransmissions, lost segments, fast retransmissions, duplicate acknowledgments. When I say to the server, send me that big fat file, Wireshark is looking at the sequence numbers of all the packets coming down. And when Wireshark sees an illogical jump in the sequence number, it's going to say, hey, previous segment lost. When all of a sudden it sees that packet show up right after that, it's going to say, out of order packet. We can recover from out of order packets as long as they're not totally all over the place and terrible. But if, let's say, the server sends down packets and the sequence number jumps, we don't see the out of order notation, then one of two things will happen in recovery. Either the client is going to start fast retransmit requesting, or the server is going to time out and just retransmit the packet. So one of two things. If you see duplicate ACK, duplicate ACK, duplicate ACK, duplicate ACK, then the receiver here is the one that noticed that the packet was missing. That's when the receiver goes, hey, where is it, where is it, where is it, where is it? If you never see duplicate ACKs, you just start seeing retransmission, retransmission, retransmission. It's the server that's timing out. And I can guarantee you, when you have more than 4 packets lost together, even if the client notices it first, the server is going to time out before the 4th one and retransmit it. Even if you're using selective acknowledgments, you're going to see this stuff in there. It gets very, very ugly. 4 packets lost altogether. All right, so we have a Windows 0 condition. When we right mouse right there, it'll take us to each of the packets where we can see that it's a Windows 0 condition. The only recovery for a Windows 0 condition is what? Yes, who said that? Who said Windows? Okay, you get it. Lucky you. Look at that. That's a power stick right there. It's a 4 gig power stick. You have to come up and get this, though. Very well done. The only recovery for a Windows 0 condition is a window update packet. That's what we want to see. There you go. Congratulations. Well done. So in here, if I look up above, Wireshark is highlighting the Windows 0 packet, and there it is. And I can tell because I can see it right here. I can see that this packet is going out, and somebody is saying, hey, look, I don't have any space available. You can't send anything to me. Stop sending. And if you follow that communications, you want to watch how long does it stay in a Windows 0 condition. So I'm going to right mouse click, and I'm going to do a conversation filter based on TCP. I basically want to pull out that one TCP conversation out of this trace. Now, it's a large trace. It's got to go through all of those. What did I get? 110,555 packets. And I've added columns in Wireshark. As you add columns to Wireshark and you start adding coloring rules, you're going to start slowing it down a bit. So you want to be aware of that. Don't go too crazy. But there is that communication, and I'm pretty sure that that person's not happy with the network. All that black background, red foreground, not a good thing. So they're probably whining and complaining, the network is slow, the network is slow, the network is slow. You know what? Part of the problem is you. You have a Windows 0 condition. Now, this is a good situation here. We have a Windows 0 condition. Immediately following that is another Windows 0 being advertised. And then that 101 millisecond delay is because the client. 101 millisecond went by, and the application picked up some of the data from the buffer, and we see a window update packet go out to say, here it is. So we now have 2,070 lousy, stinking, pathetic bytes available. That's terrible. Ick. Whatever machine that is, it's poorly configured. Let's just find a little bit more information about that particular host. If we look in the TCP header of that host, that's why. Okay, that host does not use window scaling at all. When you see that the window size that's being advertised is the same as the calculated one, that client is not using window scaling at all. Now, if we didn't get the handshake, we wouldn't really be sure. Window scaling is set up in the handshake. Always make sure that when you're going to capture and troubleshoot, you start Wireshark running and then say, okay, Fred, go ahead and show me what you mean when you surf porn. It's really slow. It's amazing. You know what? I did a job once. This is really bad. The IT team should know I'm listening to all the packets all the time. And there's a guy in there looking up some fetish site while I'm doing the live analysis. There's this fetish site coming up on all this stuff. And I'm sitting there going, I cannot believe you're looking up stuff on a fetish site. And you see this one intern in the room in the back going, oh, weird kid. Okay. Well, I guess everything's relative. I don't know. Anyway, so that's the expert system. You want to watch for this Windows 0 condition. I want you to watch for this. Now, there is something else that's really ugly out there, and I'm going to open up this trace file. This is the big one. Libraries. Let me go to my master. I'm going to go to my master trace file directory. Now, this trace file that I'm going to show you, it's on the lab kit already, but I just want to make sure I've got a nice clean version that I'm going to pull up for you here. Okay. If you saw me last year, you saw me open up this trace file. So if you saw me here last year, I'm going to get rid of that filter up there. I want to see all these packets. Okay, we can see there is a SYN, a SYNAC, and the ACK. I'm going to look at the handshake. Always pay attention to the handshakes. If people are complaining about performance, go look at the handshake. How is it established? Do you use selective acknowledgments? Do you use window scaling? How are you set up? So in the options of the TCP header, I want you to watch for that garbage. Those no operation, no operation, no operation, no operation, 4 of them in a row. Anytime you see 4 of them in a row, you've got an infrastructure problem. You've got a router somewhere in the infrastructure, or you've got a firewall product somewhere in the infrastructure, and as this SYN packet went through this device, it said, oh, you think you want to support something? I don't think so. I'm going to pad it out with all zeros here, all these no-ops in there. This originator of the packet said, I support selective acknowledgments. And that infrastructure device said, no, you don't. It went into the TCP header and altered that header to put in these NOPs. Now, these NOPs are now noted in the expert system. So that's from SharkFest last year. I've been talking about this for a while, how bad this is. And one of the developers was in the room. He said, well, why don't I make an expert system for it? It's like, that's great, fabulous. So here's what a NOP is. It's just a 0-1. 0-1, 0-1, 0-1, 0-1 together means we have a problem in the TCP options. You've got infrastructure device playing around. Now, 3 weeks ago, we started seeing the other one, end of line. 4 end of lines, and we have the same infrastructure device, but they're trying to get away from being detected now. Little stinkers, okay? So this is how you're going to detect those 4 end of lines. You go into the options area right there. And you'll see down below, it says tcp.options is the name of that field. All you have to do is build a coloring rule, and I'll build it right here for you. You say new, and the name of it is T- for troubleshooting, T-, and this is 4 end of lines. Oh, that's not even a T at the beginning. Hang on. Okay, I can't type. I never have been able to. All right, so the syntax is tcp.options contains quote 00 colon 00 colon 00 colon 00 end quote. You give it a background color of butt ugly orange. Orange. You say OK. And the last thing we do is we move our butt uglies up. So up, 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 up. I've got to finish up. OK, OK, I know. OK. So right there, I've moved it up to the top, and I'm going to say OK. I'm going to move my cursor away from this. Oh. Somehow it didn't catch that. Hang on, hang on. I've got to make sure that it's perfect. Oh, I'm sorry. That's right. Because this one has the no options. It doesn't have the end of line. It has the NOPs, the 0, 1s. I'm going to enhance it so it'll catch both of them at the same time. I'm just going to say, or frame contains, quote, 01 colon 01 colon 01 colon 01, end quote. OK. So I'm looking for just TCP options that have either a string of 4 zeros or 4 ones. Dang you. Oh, did I typo it? Okay. Oh, whoops, I don't want frame contains, my apologies, sorry, TCP options. I'm really lazy, I always do frame contains Nessus, frame contains this, frame contains that. It's tcp.options contains. God dang it, hang on. Oh, I know why, I'm sorry. When you put in quotes, it means it's text. These are not text, this is just a byte string. Get rid of the quotes when you're doing hex. That's another bad habit, here we go. So if I said frame contains Nessus, I would put the word Nessus inside of quotes, but not when I'm just doing bytes, so here we go. Gosh, finally, D's. Ever worked with, oh, thanks, that gets applause. All right, the last thing I'm gonna do, you guys, I just wanna finish up going through the list, because there's a bunch of these that I've shown you already. Create your butt ugly coloring rules, and make sure you move your butt uglies to the top so they get caught before Wireshark's default coloring rules, because they're processed in order. Also, use include and exclude filters. On the lab kit, you're going to see me building these display filters to show you how that works. Put the exclamation point to say, I'm not interested in ARP traffic. I'm not interested in this IP address traffic. Choose the right capture location, as I mentioned before. Be as close to the complaining user as you can possibly be. You could use a full duplex tap right in front of Fred's workstation. That's great. If you do port spanning, just be aware you don't get any MAC layer errors. You won't get any MAC layer errors if you do port spanning. Switches will not forward that to you. So I like using full duplex taps. Wireless, I showed you air PCAP adapters. The last piece here is just you should master the skill of T-Shark, and tomorrow I have a class on T-Shark where I'm going to be doing nothing but command line capture, because there are times when Wireshark cannot keep up, and you'll start dropping packets. At that point, you got to go to T-Shark to do all your capture, but you use Wireshark to do your analysis. There's some samples in the slides. Remember, tons of stuff in the lab kit. Go run down and get your lab kits now before they run out, and I will see you tomorrow, everybody. Thank you.